In the second unit of lecture 1, we just go more in detail about the robot components. First of all, what is a good definition of robotics? Robotics is usually defined as the intelligent connection of perception to action, which is the same kind of feedback principle which regulates our vital function in the human brain. So basically, when we look at the components of a robot, we have a mechanical part, and this is typically an arm, to manipulate the object, but could also be a vehicle to move the system around. Then we have the action, which is provided by some actuators, typically there are motors, so the commands are really implemented by this kind of actuating action. And then we have to really perceive the environment, so we need sensor, so we have to react to the environment. And that's why we need both proprioceptive sensors to measure the internal state of the robot and exteroceptive sensor to gather some information about the environment. But the kernel of all this is the intelligence of the robotic system. And this is the control system that really correlates the information from the sensors and try to design and to execute the best action to carry out a given task. So if we look at the components of a robot manipulator, typically we distinguish an arm, which is a sequence of rigid bodies, links, which are interconnected by joints, like the human arm. So this would be like the arm, the forearm, two links, and this would be the shoulder joint, and this would be the elbow joint. And typically the joints could be of two types: prismatic, if there is a translational motion, or revolute, if there is a rotational motion. And you can really infer that the most dexterous actions are obtained by using revolute joint compared to the prismatic joints. So this is the supporting structure of the arm. But not only do we need to position the system into the workspace, but also we need to orientate the system. That's why we need a way to change the orientation of the system, to change the attitude. So we need the wrist. And the wrist has additional degrees of freedom that allow us to change the orientation. And depending on the specific application, we also need some kind of hand effectors, be it a gripper or be it maybe a multi-finger hands in the most advanced application. Let's take a look at the geometries which are typically used for the supporting structure, for the arm. Typically here we need 3 degrees of freedom, because 3 degrees of freedom are needed to position a rigid body in space. So we can have a Cartesian geometry in which we have all linear motions. We can have a cylindrical geometry in which one of the prismatic joint is replaced with a revolute joint and there is a cylindrical symmetry. We can have a spherical geometry in which there are 2 revolute joints and 1 prismatic joint providing the stroke. And also we can have another geometry which has gained quite a bit of success into the industrial design. This is the SCARA geometry. SCARA is an acronym that stands for Selective Compliant Assembly Robot Arm. So this geometry has 4 joints, 3 revolute and 1 prismatic, and is typically used to move objects fast in the horizontal plane and to do some assembly from the vertical direction. But in everybody's opinion, the most dexterous structure is the anthropomorphic structure, which is really inspired by the human arm. So in anthropomorphic structure, we have 3 level joints: a base joint, a shoulder joint, and an elbow joint. And this is the most compact and the most dexterous structure. So this is the arm, but also we can have some kind of design which is specifically thought to be able to lift up heavy payloads. This is the same kind of anthropomorphic structure, but as a parallelogram. So it's a kind of closed chain mechanism between the shoulder joint and the elbow joint. And this is useful if you want the structure to be kind of stiffer and to be able to pick up really heavy loads. Another geometry which has gained quite a bit of popularity is the parallel geometry. Parallel geometry, there are like 2 plates, like a base and an end effector, and those are connected typically by linear joints. So the difference between this structure and the serial kinematic chain structure is that the parallel structure has a very small workspace, but it's very fast motion, and you can really carry out motion with high precision. So this was the supporting structure. As I say, to complete the manipulator, we have a wrist and we have an end effector. Speaking about the wrist, as I said, we need 3 additional degrees of freedom to change arbitrarily the orientation of a rigid body in space. That's why typically wrists have 3 joints, and they must be 3 revolute joints, clearly. They can't be prismatic joints. And when we speak about this wrist, the most dexterous structure is the spherical wrist. A spherical wrist is obtained when the three axes of the revolute joints intersect at the same point. And as you will learn in lecture 4, which is devoted to direct kinematics, we will learn that thanks to this kind of arrangement, there is a very nice kinematic decoupling between the position and orientation. And this is very, very useful to solve not only the direct kinematics problem, but as we will learn, also to solve the inverse kinematic problem. Finally, the end effector. The end effector really depends on the task. So you can have a simple gripper with two jaws if you really want to pick up object and manipulate from one location to the other, or you can have really the most advanced end effector, and I'm speaking about like 3 fingers or 4 fingers or 5 multi-finger hands. Of course, compared to the arms and compared to the grippers, I wouldn't say that multi-degree of freedom hands are really commercial products. They are still in the stage of prototypes. You can buy some hands, but you're going to spend a lot of money on them.